Okay, back to the VCAA 2021 physics exam section B, and question 15, so it's about photoelectric. Experiment is carried out by students. They measure the threshold frequency required for photo emission to be 6.5 by 10 to the 14. And the work function to be 3.2 by 10 to the minus 19. All right, so threshold frequency, that's F naught. And the work function, using the students' measurements, what would they calculate Planck's constant? Outline your reasoning and show all your work and give your answer in joule per second. All right, so what we know is that the threshold frequency, F0 is 6.5 by 10 to the 14. And we know that the work function is 3.2 by 10 to the minus 19. And the units that we're given, they're standard units. All right, so what do we know? Well, there's a couple of different approaches. One of them is that we know that the work function is Planck's constant times the threshold frequency. So the work function, which is 3.2 by 10 to the minus 19 joule, is equal to Planck's constant times the threshold frequency, which is that. And so our Planck's constant then would be 3.2 by 10 to the minus 19 divided by 6.5 by 10 to the 14, which works out to be 4.92 by 10 to the minus 34. And given we've used our standard units, that's already in joule seconds. All right, so in terms of numbers of figures in the answer, well, there's 2 here, there's 2 there, so we better give 2. So our final answer that we're going to write in the box here is 4.9 by 10 to the minus 30, minus 34. There we go, that's better. Outline your reasoning and show all your working out. Well, I think there's the reasoning, and the working out is that there. All right, question 16. Light can be described by a wave model, also a particle or photon model. The rapid emission of photoelectrons at very low intensity supports one of these models, but not the other. All right, so key thing we're talking about is rapid emission of photoelectrons at very low light intensity. All right, so the question is, which one is it, the wave or the particle model? It's 2 marks, so we've got to give some sort of reason. The model supported, and we're also told to give a reason, model supported is the particle model. All right, so again, we need to be specific to the question. And so the particle photon gives up all its energy and photoelectron is emitted. And a photoelectron is emitted if the photon energy is above that of the work function. All right. Now, rapid emission at low light. So that's part of it. The other part of it we can say is that it doesn't rely on the number of photons. Which would be the intensity. Thus, a photon electron, can be emitted rapidly. All right, so you need something along those lines. So we've got to be specific and include those things there that's in the question, the rapid emission at low light intensities. All right, which I have done. So there it said doesn't rely on the number of photons in the sense, thus the photoelectron can be emitted rapidly. All right, we could expand on that again. Get your teacher's view on that. But you do have to be specific to the stuff that they've mentioned here that I've underlined. All right, question 17. Space sail is mounted in a tiny interstellar cylindrical probe that relies on momentum of photons from a nearby star to do a propulsive force. Photons strike the sail at 90 degrees and reflect elastically. Scientists need to calculate the force exerted by the photons, which have a frequency of 7 by 10 to the 15. All right, reflected elastically, that's handy because that means no energy loss. All right, so it says show here, that means we've got to have some working out. And it says show the momentum of this frequency photon is equal to that. All right, so again, formula sheets, got stuff on our formula sheets to do with wave nature of light, and it says that the momentum is h on lambda. All right, now we don't have the wavelength, we have the frequency, so we've got to use the other version, which is hf on c, the speed of light, seeing as they're photons. All right, so that is 6.63 by 10 to the minus 34 for the Planck's constant. The frequency is there, 7 by 10 to the 15. And the speed of light, of course, is 3 by 10 to the 8. And we put all of that in our calculator. And when we do that, we get 1.547 by 10 to the minus 26, which, of course, when we round that to 2 decimal places, it's 1.55 by 10 to the minus 26. It's all standard units that we've used, so that's kilogram meters per second. All right, so you need to give all of that because you've got to show. All right, so it says that 2 by 10 to the 18 photons of this frequency strike the sail every second. Calculate the force the reflecting photon exerts on the sail. show your working, give your answer to two significant figures. All right, so there's 3 marks there, so we've got to do a bit of working out. All right, so this many every second, and we want to calculate the force. All right, so what have we got? We've got impulse, because they strike the screen, so there's an impulse. So impulse is the average force over the time. Now the time we've got here is every second, average force. Now also impulse is change in momentum. So what is the change in momentum? All right, so these things are reflecting, so they're coming in and then they're reflecting back. So our change in momentum, because they reflect and they go in completely 180 degrees the opposite direction, that means that the change in momentum would be 2 lots of this momentum that we've got up here in part A. All right, so yes, I know that change in momentum is our final minus our initial. The sizes of these are the same, but completely 180 degrees the opposite direction. So that's why in this case it's 2 lots of the momentum. All right, so 2 lots of that, and 2 lots of that is 3.11 by 10 to the minus 26. Now that's for each photon. And what we have is 2 by 10 to the 18 photons. So our total change in momentum then is 2 by 10 to the 18 lots of the 3.11 by 10 to the minus 26, which when I look at that, it's 6.2 by 10 to the minus 8. All right, average force we're after. So what we know is, so if I put these two things together, the average force times the time would be the change in momentum. And so our average force times 1 is 6.2 by 10 to the minus 8. So my average force then is 6.2 by 10 to the minus 8 Newton. And there it is. All right, so you're asked to calculate, asked to show you working, 2 figures in our answer. All right, so 3 marks, so there's a bit of stuff that you need to show if you're going to get your 3 marks. All right, next question is question 18, but I think I'll leave that for another video because I think this one's gone on long enough. So as always, make sure that you get the opinion of your teacher. Just remember, this is my take on these, and also read the examiner's reports as well.